Welcome, students, to the first in my series of special topics videos. My purpose in designing these is to help second-year organic chemistry students to review the concepts that they should have learned thus far over the course of their entire year of organic chemistry. My focus will be on topics that are most relevant for student entrance exams such as the MCAT, the DAT, the PCAT, the GRE, and so forth. My intended audience, of course, is students who are nearing the end of their second semester of organic chemistry. Now, although I've written all of the questions in this presentation myself, they are based on standardized exam questions that I've personally encountered. I'm Dr. Mike Christiansen from Utah State University's regional campus in Vernal, Utah, and I endorse this message. Today I'll be teaching you about IUPAC naming and the chemical properties of matter. Because my intended audience is students nearing the end of their second semester of organic chemistry, I won't be spending excessive time reviewing lots of details and minutiae from past organic chemistry lectures. I'm assuming that you already know these concepts. If not, then I invite you to review my previous video lectures or consult other organic chemistry learning material you may have access to. By the end of this lecture, you should be able to do the following: produce IUPAC names for simple organic molecules and recognize the IUPAC suffixes for different functional groups. Identify any atom's hybridization and explain, in terms of atomic and molecular orbitals, what that actually means. Arrange related molecules in order of highest to lowest boiling point, or vice versa. Arrange related molecules in order of highest to lowest acidity, or vice versa. Identify an empirical formula's number of degrees of unsaturation, and understand what that means. For a series of reactions, predict which one will be the most exothermic and which will be the most endothermic. Arrange related molecules in order of highest to lowest solubility, or vice versa, in a given solvent. And last, compare two isomers and identify their isomeric relationship. We'll first address the systematic IUPAC naming of organic molecules. As you already know, we give simple names to alkanes whose general formula is CnH2n+2, according to the number of carbons found in their parent chain, as this table indicates. Thus we see that a 1-carbon long alkane is called methane, 2-carbon long is ethane, then propane, butane, etc. In the world of organic chemistry, each type of reacting group, called a functional group, has a different suffix appended to the end of its parent chain name, which varies according to the functional group's identity. For example, we can see in this column to the left a list of various functional groups. Carboxylic acid, which has this generic formula. I've shown in this column several different example names of sample carboxylic acids, such as ethanoic acid, propanoic acid, butanoic acid, etc. Thus you can see that if you have a 2-carbon long chain that's a carboxylic acid, we call it ethanoic acid. We begin with ethane, which is the base name for a 2-carbon long alkane. We remove the E at the end of ethane and add the suffix oic acid. For an ester, we name the R' group dangling off of this side at first, and then we take the parent chain name, remove the letter E, and add the suffix O8. For nitriles, right here, we count how many carbons there are that include this carbon triple bonded to the nitrogen, and use that as the base name for the nitrile. Thus, if I had a 2-carbon long nitrile, it would be called ethane nitrile. A 3-carbon long would be propane nitrile. Thus, we could say that nitrile is the suffix for a nitrile functional group. I hope that makes sense. So you guys might ask the question, what do we do if we have multiple functional groups in one molecule? For example, let's pretend that I have a single molecule that contains an alcohol somewhere and an aldehyde somewhere else. Which functional group do I choose to be the compound's parent name? The answer is whichever functional group has higher priority. So yes, this table that I have here shows a list of various functional groups sorted in order of IUPAC priority. And once the parent functional group, or the highest priority functional group, is determined, all of the remaining functional groups in the molecule are considered substituents. Now, I should mention that this is not an exhaustive list of all the functional groups out there, but it does contain probably all the functional groups that you guys will encounter on any of your standardized exams. I've shown here, once again in this column, generic structures for these different functional groups. I've included several example names here in the central column. Now, if you have any confusion with these, then frankly, I invite you to slap yourself for not remembering the stuff that you should have remembered from previous lectures on this subject. And then I invite you to look up more details on the internet yourselves. Now, generally speaking, the higher the oxidation state of a functional group, usually the higher priority that is. For example, you can see that this carboxylic acid and esters, which have a high oxidation state, that is, multiple bonds to oxygen, are higher priority than an alcohol, which has a lower oxidation state. Now, there are some obvious exceptions. For example, this nitro, which is a highly oxidized nitrogen atom, is all the way at the bottom of the priority group list. Now, since they don't seem to follow any clear logic, I personally can't help but wonder if this functional group priority list was selected by a bunch of inebriated Frenchmen with a dartboard. Now, for your reference, I've included a column here that shows you what to name a particular functional group if it's considered to be a substituent. That is, if it's a functional group inside a molecule that contains also a higher priority functional group. In the example that I cited earlier, a molecule that has an aldehyde somewhere and an alcohol somewhere else, we go down the priority list and we see that aldehyde is higher up than alcohol. Thus, aldehyde would be the parent name that we would use: ethanal, propanal, butanal, etc. Alcohol would be considered a substituent to that. When alcohol is a substituent, we name it hydroxy. Thus, if we had a 5-carbon long aldehyde that had an alcohol on carbon 3, we would call it 3-hydroxypentanal, the aldehyde being the functional group. Now, if you happen to have a molecule where the alcohol is the highest priority, then the parent name or suffix is all: methanol, ethanol, propanol, etc. I invite you to conjure up some of your own problems if you need to get some practice doing more of these. Alright. Now, I want you guys to remember two other nuances. First, we call di-substituted cyclic molecules cis if their two substituents are pointing in the same direction, and trans if their two substituents are pointing in opposite directions. Now, here are two examples that I've shown here. You're welcome to study these names and make sure that they make sense to you. Second, alkenes are called Z-alkenes if the highest priority substituents coming off the double bond are on the same side, or the same side as each other. They're called E-alkenes if the highest priority substituents are on opposite sides of the double bond of each other, or in other words, opposite sides. So remember, Z is if they're on the same side, and E is if they're on opposite sides of each other. I hope you found that joke as funny as I did. You feel good about this? Good. Let's do some problems. So here are some problems, sample questions that are based on actual standardized exam questions I've encountered. Which of the following are considered terminal functional groups? That is, functional groups that we would find at the terminus, or the end of a chain. Next lecture question. What is the correct name of the Hayworth projection shown here? Is it alpha D-glucose, beta D-glucose, alpha L-glucose, or sigma L-glucose? Now you should remember this from our chapter 22 lectures on carbohydrates, which we had recently. Next lecture question. What is the correct structure for trans 1-ethoxy 2-propoxycyclopentane? And our last question, the IUPAC name for the structure shown here ends with what suffix? I should pause here and look at this molecule. It's pretty hairy. It's got lots of functional groups here. But the way we answer this question is by finding which of these functional groups has the highest priority. You can consult the previous slide if you want to figure that out. But whatever functional group has the highest priority of all the functional groups in this molecule, that is going to be the suffix to which we would attribute the IUPAC name for this. Now, as you're probably deducing from me rambling on about these questions, I am not going to give you any of the answers to them. I'm going to let you see if you can figure them out for yourselves. When we meet together in class, I'll give you the chance to answer them again, and maybe I'll help you a little bit more if you ask nicely. Here are some more questions. What is the IUPAC name for L-glyceraldehyde, which is shown here? Next, the compound shown here is reacted in a way that opens the ring by breaking the carbon-carbon double bond to give an unsaturated carbon chain. The carbonyl is left unaffected. What is the name of this new compound? Now, I should mention parenthetically that this particular question, which is based very closely on a standardized question that I have encountered, is slightly ridiculous because there's no reaction that I personally know of that will do this type of transformation they're describing at all, actually. I really don't know of any, so it's obvious that some of the standardized questions are written by people who are not organic chemists. Next lecture question. Triglycerides include which of the following? Now, triglyceride structure is one that I haven't really covered well in organic chemistry in the past, but I thought I'd give you a hand by showing you what a triglyceride looks like. Triglyceride is a fancy name for a fat or an oil. The only difference practically between a fat and oil is that an oil is a liquid at room temperature and a fat is a solid at room temperature. And that difference is determined by how long and how saturated these R groups are. The longer the R groups, the higher the molecular weight, and generally it tends to be more and more of a solid, hence a fat. Shorter the R groups or more double or triple bonds in them, they tend to be more oils. So that's a triglyceride. Triglycerides are made up of this compound, glycerol, and mixtures of fatty acids. I should point out that you can do this reaction in reverse. If you take a triglyceride and treat it with sodium hydroxide, you can actually hydrolyze off all of these ester bonds to get glycerol. And the deprotonated sodium salts of the fatty acids, which are in fact the structures of soap. And that is how soap is made. I'll now readdress this ever-forgettable topic of atomic hybridization. Now, there are two different ways of learning hybridization, the easy way and the hard way. I, of course, prefer the easy way for everything. But on this topic, to be quite honest, you really have to learn both in order to understand what's going on. So I'm going to teach them both to you. First, we'll talk about the easy way. If I'm ever asked to determine an atom's hybridization, all I do is count how many things are around that atom. You can see me giving you this table right here. Now, the number of things around an atom, I should say, refers to how many other atoms or lone pairs are around them. So when I say a thing, I'm talking about another atom or a lone pair. So we count how many things there are, and then we memorize this chart. 2 things is an sp hybridized center, 3 things sp2, and 4 is sp3. And that should get us deep enough to be able to answer any of the types of questions that you'd encounter on a standardized exam on this subject. Let's see if we can look at some examples. What is the hybridization of each of the indicated atoms? Let's start at this one. See this carbon? We're going to count how many things are around it. By things, I mean atoms or lone pairs. This carbon has a hydrogen, a hydrogen, a hydrogen, a hydrogen. I'll hold up that. I count to 4. There's 4 hydrogens. So what's its hybridization? It's sp3. 1, 2, 3. sp3. Let's look at the hybridization of this carbon atom. How many things are around it? I've got a hydrogen, and an oxygen. Now this is one of those things that some students get confused about. They think that because there's a double bond here, I'm going to count that somehow as more than one thing. You do not. All we do is count how many things are around it. A hydrogen, and an oxygen. The hybridization of that is sp2. Let's see if we can figure out the hybridization of this oxygen. How many things are around it? It's got a carbon down here, lone pairs over here, and lone pairs over there. sp 2p2. See that? What's the hybridization of this carbon atom? Once again, we count how many things are around it. We don't care that there's a triple bond or a double bond or a quadruple bond or a sextuple bond. That is irrelevant. We just look and count how many things are around it. One hydrogen to the left and a carbon to the right. There's only two, so it is sp. Does that make sense? This is the easy way to determine an atom's hybridization. Now, as I indicated before, I am going to teach you the hard way. But before I get to that, I want to also re-solidify in your minds what we've taught before about atomic bond angles. I want you to tell me, what are the indicated bond angles? In this molecule that we decided has an sp3 hybridized carbon in the center, what is the bond angle between all of these hydrogens in this tetrahedral structure? You should have remembered it is 109.5. What about right here? This carbon only has three things around it in a trigonal plane structure. What's the bond angle? It's 120. And the bond angle right here, this carbon is in a nice straight line. It's 180. Thus we can see that an sp3 hybridized carbon will try to get its four groups to be around 109.5. An sp2 hybridized carbon will try to get its groups to be 120. And an sp hybridized carbon will try to get its groups to be around 180. It's not always dead on those numbers, but it tries as best as it can to match them. Now to the hard way, which is my way of saying now I'm going to actually teach you what's really going on. I'll of course be talking about orbitals, which is a subject that often makes people poop their pants with fear. Please don't do that, because I don't think anyone would appreciate cleaning up the mess. To simplify things, I want you guys to imagine that orbitals are really nothing more than a region of space that electrons can occupy. Orbitals are in essence just empty parking places for electrons to go into. Different orbitals, of course, have different shapes. S orbitals are shaped like spheres, and p orbitals are shaped like cute little dumbbells. Now, as you should have learned back in general chemistry, every element has its own electron configuration, which is a subject that I won't review here. Carbon's electron configuration, of course, is 1s2, 2s2, 2p2. Now, carbon's valence orbitals are the ones that have the highest number, this 2s orbital and this 2p orbital. You count up the number of electrons occupying those, it adds up to 1, 2, 3, 4. So that means that carbon has 4 total valence electrons. Now let's see if we can assemble a carbon atom one layer at a time. We'll imagine that carbon's nucleus looks like this. This is where its neutrons and protons are located. This nucleus is surrounded by a 1s orbital. Now if you look up here, you see how it says there are 2 electrons that occupy that 1s orbital? There they are. These are core electrons. Now outside this layer we see a slightly larger 2s orbital. Over here in the electron configuration it says there are 2 electrons that occupy that 2s orbital. There they are. Now these are 2 of carbon's valence electrons. Outside of this layer, we see carbon's 3 individual 2p orbitals, which straddle the x, y, and z axes 90 degrees apart from each other. Now each of carbon's if we look over here, you'll see that the electron configuration indicates that there are 2 electrons in carbon's 2p orbitals. Where do those go? They go right here and right here. The third 2p dumbbell right here remains unoccupied. So let's pretend that carbon wants to bond with 4 separate hydrogen atoms to form methane, the molecule shown here. Now once again you'll remember that the bond angle in this tetrahedral structure is 109.5 degrees. So here come our 4 individual hydrogen atoms ready to bond with carbon. In order to form a bond, each of these hydrogen atoms, which has an individual 1s orbital filled with a single electron, has to overlap with carbon's valence orbital somehow, so that their joint electrons can be shared in those molecular orbitals. Now look at this. How in the world are these hydrogen atoms going to be able to overlap with carbon's 2p and 2s orbitals? Where could they go? Well, we could imagine this hydrogen atom right here might be able to overlap with the bottom of this p orbital. Okay. And this hydrogen atom over here could potentially overlap with this p orbital, and this hydrogen atom could overlap with this p orbital. But if it did that, now all three of these hydrogen atoms have overlapped with three of these p orbitals. What's left for this poor hydrogen atom over here? Where can he go? Well, the only thing he could overlap with is the 2s orbital, which is kind of a little bit located, squished in here in the interior. So he'd have to like kind of squish down in there. And that might create some real problems for him to be able to fit into that hole. There's another problem here too. Each of these p orbitals are located 90 degrees apart, not 109.5. So even if these three hydrogen atoms did latch on and overlap with these p orbitals, they're not going to be 109.5 apart. They're going to be 90 degrees apart. And then this hydrogen atom is going to have to somehow squish down so that it can fit into this 2s orbital here. This whole situation stinks, much like methane gas itself. So what in the world can carbon do? Well, what carbon does is it takes its three 2p orbitals, shown here, and its one 2s orbital, and it combines them. So if you could imagine that these four different orbitals, the three 2p orbitals and this one 2s orbital, if these were all made out of molding clay, and I took them in my hands and squished them all together, and then I took all of that molding clay and separated it out equally into four separate orbitals that are all equal size and shape, that's essentially what carbon's doing. It's taking these three individual 2p orbitals, this one 2s orbital, squishing them together, and separating them out into four separate and equal sp3 orbitals. Carbon now places each of these new sp3 orbitals together in this kind of three-dimensional form. And guess what the bond angle is between them? 109.5. Carbon can put its four valence electrons in each in one of these four sp3 orbitals. Now what can happen? Well, now each of these four hydrogen atoms can come right in there, 109.5 degrees apart, overlap with these four sp3 orbitals, and form a nice, beautiful molecule of methane. Isn't that pretty? That's what orbital hybridization is. The word hybrid comes from a Latin root that essentially means mixing or combining. So what it's doing is it's taking an s orbital and some number of p orbitals and squishing them together to make new orbitals. Does that make sense? Well, let's see if we can figure out and apply it to a different kind of hybridization. As you might remember, the hybridization of this carbon is sp2, and the bond angle should be about 120 degrees. So what does that mean? Well, it means that carbon has combined its 2s orbital and only two of its 2p orbitals together in this hybridization. Let's see if we can take a look at that. So carbon's taken two of its 2p orbitals and its one 2s orbital, squished them together, woo, and then made three individual equal sp2 orbitals like that. These three individual sp2 orbitals are then laid down in a trigonal planar structure like this. This is supposed to be all in a plane with a beautiful 120 degree angle separating each of these lobes. Now you'll notice when we contrast this pattern with what we saw in the previous slide that carbon in this case left one of its 2p orbitals out. It only used up two of these in this hybridization process. So what happened to the third 2p orbital? Where is it? It's right here. It goes above and below the plane of these three individual sp2 orbitals, 90 degrees perpendicular to that plane. That's what an sp2 hybridized carbon center looks like. Our carbon atom is now hybridized and ready to go. It places its 4 valence electrons, 3 individually, into its 3 sp2 orbitals, and 1 into its perpendicular 2p orbital, which was left unused in the hybridization. Now oxygen, which is also sp2 hybridized in this molecule, comes in. Oxygen has 6 valence electrons, which occupies orbitals like this. These 2 electrons, which are coupled here in one of these sp2 hybridized orbitals, as well as these, represent these lone pairs dangling off of the oxygen like so. Now, oxygen comes in, and these 2 atoms overlap to form this. This bond between oxygen and carbon here in the center is a sigma bond. This perpendicular overlapping bond between the unused 2p orbitals in both atoms is called a pi bond. Now, I don't want you to be confused here. A pi bond kind of looks like 2 bonds. There's a line on top and a line on bottom. Don't think of that as 2 bonds. That is 1 pi bond. It is a pi bond, or a bond formed by unused 2p orbitals overlapping. It is not as strong as a sigma bond. Now at this juncture, the hydrogens can come in, overlap with these orbitals in the carbon atom, and form this molecule that we have right here. Now let's do the same process for an sp hybridized molecule, which has a 180-degree bond angle right here. The fact that these carbon atoms are sp hybridized implies that they've used up one of their s orbital and one of their p's, and they've left the other 2 p's unused in the hybridization. So let's take a look at that. We've taken one of our 2p orbitals, one of our 2s orbitals, and we only have one, combine them to form 2 sp orbitals. When these sp orbitals are thrown together on the carbon atom, they form a nice 180-degree angle linearly like this. So what in the world happens here? Well, the unused 2p orbitals go perpendicular to the plane, 90 degrees apart from each other. So once again, let's go back. This carbon atom used one of its 2p orbitals. The other 2 2p orbitals remain unused, being perpendicular to each other and to the plane, which is occupied by these 2 individual sp orbitals. So what occurs next? Well, here are my 2 carbon atoms, both sp hybridized, with their remaining unused 2p orbitals lying perpendicular to each other, as shown here. At this point, they fill their orbitals with their respective valence electrons. They then overlap like so. Now this bond between the carbon and the other carbon is a sigma bond. These perpendicular overlapping bonds are each separate pi bonds. Once again, this circuit here is one pi bond, and this circuit here is a second pi bond. That represents the triple bond. These hydrogen atoms can now come in, overlap with these lobes dangling off of the end, ultimately making this molecule, which is called ethine. Do you feel comfortable about this? Good. Let's do some problems. How many sigma and pi bonds are there in the following molecule? Next question. In a carbon-carbon double bond, hybridization occurs between the s orbital and 1p orbital, between the s orbital and 2p orbitals, between the s orbital and 3p orbitals, between 1s and... Man, I got to take a nap. Here's the deal. This question is kind of a convoluted way of really asking you what is the hybridization of these carbons in a carbon-carbon double bond. Can you figure out the answer? I hope so. Next question. Pi bonds are formed by which of the following orbitals? Next question. How would one best describe the orbitals required to form a pi bond? I hope based on what we've just learned, you can figure that out. And the final question, what is the hybridization of beryllium in a beryllium H2 molecule? Now, if you don't know the answer to these, don't worry. You'll get the chance to learn them when we do these together in class. And this will be the point where I'm going to stop our lecture for today. But I want you guys to stay tuned for our next lecture because it is going to blow your minds. Until then, have an enjoyable evening.